Hi, everyone. I'm glad to present our work, What Can Crypto Do for Decentralized Mechanism Design? This is a joint work with Elaine and Chung from Carnegie Mellon University. So in this work, we focus on transaction fee mechanism. What is a transaction fee mechanism? As we know, real estate on the blockchain is really expensive. So users want to have their transactions confirmed, and often users would have to compete with each other to get their transactions confirmed. We can view this as an auction where the miner is selling the slots in the block to the users. In this case, we need to run a so-called transaction fee mechanism to decide which transactions to confirm, how much they pay, and how much the miner gets. For example, Bitcoin employs a simple first price auction. Let's just assume that the block size is 1. The highest bid will be confirmed, and it pays its own bid. All the payment go to the miner. As we have learned from classical algorithmic game theory, a first price auction is not good because it incentivizes users to bid untruthfully. For example, it may be my best strategy to bid barely enough to be the top bid. So I will get confirmed and pay the least possible price. What's interesting here is that all classical mechanisms we know fail. For example, we know that second price auctions are a golden standard in classical mechanism design because they incentivize the bidders to bid truthfully. So why not just implement second price auction? What can go wrong here? For example, in second price auction, the highest bid 9 will be confirmed, and it pays the second highest bid 6 as the price to the miner. However, on blockchain, a strategic miner can inject a fake transaction with bid, let's say 8. Now the confirmed bid 9 has to pay 8 to the miner rather than 6. So miner can increase its gain by deviating. More generally, in classical setting, we typically assume that the miner or the auctioneer is fully trusted, and we care about designing mechanisms that incentivizes the users to bid truthfully. In decentralized environment, however, the miner may also have incentive to cheat, and it may not implement the mechanism faithfully. That's why the classical mechanisms are not a good fit here. So we want to ask this question: what makes a dream transaction fee mechanism? What properties or the incentive aspects of transaction fee mechanism we want to have to design an ideal transaction fee mechanism? Recently, a line of work has looked into this space, and most of these work agree that the following 3 properties are important. The first one is called user incentive compatibility, abbreviated as UIC. It guarantees that a user does not want to deviate, so a user will bid truthfully. And this is the same notion as in classical mechanism design. In addition to this, we want to make sure that we have miner incentive compatibility, or equivalently, we want to guarantee that the miner does not have an incentive to deviate. So the miner want to implement the mechanism honestly. Last but not the least, in the blockchain environment, it is easy for players to form binding smart contracts. In particular, they can rely on smart contracts as an enforcement mechanism to split up their joint gains. Therefore, we also want a third property called side contract proofness, or SCP for short. In particular, suppose that a miner forms a coalition with C users, and the coalition is aiming to maximize their joint gain. In this case, the coalition's best response is to follow the protocol honestly. Among these 3 properties, the last 2 arises in this new decentralized environment. And these are the new challenges we are facing that makes transaction fee mechanism depart from classical mechanism design. In Tim Roughgarden's EC21 work, he asked the question, can we have a dream transaction fee mechanism? So the closest we have come to in terms of a dream transaction fee mechanism is actually Ethereum's EIP 1559. Let me quickly mention how it works. it gracefully switched between two modes of operation. When the network is congested, namely when there are a lot of transactions waiting to be confirmed, it approximates the behavior of a first price auction, which is not good, as we mentioned. When the network is uncongested, however, their mechanism approximates a simple posted price auction. In other words, there is a take it or leave it offer called the posted price. If you bid higher than the posted price, you get confirmed and you pay the posted price. If you bid lower than the posted price, you would not be confirmed. And here, all payments are burned rather than paid to the miner. So Team Rothgarten proved that EIP 1559 satisfies all three properties we want if we are willing to assume infinite block size, or equivalently when there is no congestion. So posted price auction is good when we have infinite block size. In reality, of course, the block size is finite and congestion will happen every now and then. In this case, we still don't know any good transaction fee mechanism. Let's consider a naive idea. Let's suppose the block size is 1. So we randomly pick a bid that is at least the posted price to confirm. It pays the posted price and all payments are burnt. So is this a good transaction fee mechanism? It actually satisfies UIC and MIC. However, it is not one SCP. So basically, a collision of a miner and a user can increase their joint gain by deviating. To see how they perform the attack, let's imagine the following case. The block size is 1 and the posted price is 5. So all the bids in the mempool is 10. So now instead of randomly choosing a bid to confirm, the miner will just confirm its occluding user friend's bid. So this increased the probability of the occluding user being confirmed from 1/5 to 1. And this increases the expected joint gain of the collision. Actually, this example captures the main idea of the impossibility result in Chung and Chi's Soda 23 work. They showed that under finite block size, no non-trivial transaction fee mechanism satisfies all three properties. By trivial, we mean that no transaction is ever confirmed in the block. So this is quite pessimistic. So in this work, we asked the question, can we use crypto to help circumvent this impossibility? Can we use crypto to force the miner to implement the mechanism faithfully? And we give a positive answer. In this work, we propose a new model called MPC-assisted model, where MPC stands for multi-party computation, a powerful cryptographic primitive. In the MPC-assisted model, instead of having a single miner implement the mechanism, we let a group of miners together to implement the mechanism. To do this, we let each user send their bid to other miners. Then, all the miners interact among themselves to run the primitive called multi-party computation based on all the bids they received. The multi-party computation computes the output of the mechanism, and it guarantees the correctness of the output as long as a majority number of miners are honest. That means the transaction fee mechanism will be honestly implemented. Note that in an honest execution, the users do not need to talk to each other. They only talk to the miners. So basically, we can view this whole box as an ideal functionality. It receives users' bid as input and gives us the output of the transaction fee mechanism. So this model enforces the correct implementation of the transaction fee mechanism. In this work, we basically show the following results. First, we show that cryptography indeed helps to circumvent the impossibility result in Chung and Chi's Soda 23 work. However, we also show that cryptography does not trivialize transaction fee mechanism. Although it enforces correct implementation of the transaction fee mechanism and thus brings the design space closer to that of classical mechanism design, but still it differs a lot from classical mechanism design. Because first here, we still care about minor user collision. And second, we allow each users and the miner may still inject fake transactions, and users can choose to drop out. These are usually not considered in classical mechanism designs. More specifically, in our paper, we give the following results. We call the model without MPC as the plain model. So previous work ruled out the possibility of a dream transaction fee mechanism in the plain model, whereas we showed that in the MPC-assisted model, we can design a dream transaction fee mechanism. However, the mechanism is only one SCP. It is not incentive compatible against miner colluding with more users. And we actually showed that this is inherent. We proved that it is impossible to have a dream transaction fee mechanism if the miner collude with two or more users, even in the MPC-assisted model. Therefore, we also consider another dimension of relaxation. What if we allow the collision to gain a little bit, but no more than epsilon more utility? In this case, under this relaxation, we show that the social welfare, the sum of the utility of all users and all miners, is unscalable in the plain model. And by scalable, we mean that if everyone double their bids, then the social welfare should double. So basically, we want the social welfare to grow linearly as the bid grows. However, in the MPC-assisted model, we give a mechanism that achieves optimal social welfare. So from this table, we can see that indeed crypto helps a lot. It makes what was originally impossible in the plain model now possible. So in the rest of the talk, I will focus on the feasibility we achieve in the MPC-assisted model. We will first see how to build a dream transaction fee mechanism in the MPC-assisted model. And we will see why it is not 2 SCP, so why it is not incentive compatible when the miner collude with 2 users. Then we'll show if we relax the notion to approximate incentive compatibility, we will be able to construct a dream transaction fee mechanism satisfying all properties, as well as achieving optimal social welfare. So now let's first look at our feasibility that is 1 SCP in the MPC-assisted model satisfies all properties. So a simple observation is that now with the MPC-assisted model, we are guaranteed that the transaction fee mechanism is implemented correctly. So the posted price auction with random selection we mentioned now becomes a good transaction fee mechanism that satisfies all properties, where we randomly choose one bid from the bid that is at least the posted price to confirm. It pays the posted price and all payments burnt. Now, since by the MPC-assisted model, we are guaranteed that the MPC guarantees that it will randomly choose a bid to confirm, so the miner cannot help its colluding user friend anymore. So now it is 1 SCP in the MPC-assisted model, and we have a dream transaction fee mechanism. However, this is not 2 SCP. That means even if the miner collude with only 2 users, they have a strategy to increase their joint gain. To see why this is the case, let's assume still that the block size is 1 and posted price is 5. And these 2 users in the orange are the 2 users in the collision. The big user has bid 10 and the small user has bid 5. So note that here, so for the small user, since its true value is 5, its utility is always 0. So for the collision to increase their joint utility, they basically want to increase the utility of the big user. To do this, the small user will choose to drop out to increase the probability of the big user being confirmed. So for example, before it drop out, the probability of the big user being confirmed is 1/5, and now it's 1/4. So this captures the idea of our impossibility proof. We can actually show that even in the MPC-assisted model, it is impossible to achieve 2 SCP, UIC, and MIC simultaneously. So to circumvent this impossibility result, we consider another dimension of relaxation. What if we allow the minor user coalition to gain a little bit more? Does that give us any feasibility? And the answer is positive. So if we consider approximate incentive compatibility, we can construct this MPC-assisted diluted posted price auction. It is UIC, MIC, and approximate to SCP. As a heads up here, I'm only given the example for two including users, but this can generalize this to arbitrary C. And the intuition behind is basically that, sure, a small user can choose to drop out to help its friend. But when the population is large, the increment is very small, so you cannot help too much. Specifically in MPC-assisted diluted posted price, what we do is as follows. So first, we choose all bids, at least the posted price, as candidates. If the number of candidates is too small, say less than a predetermined threshold T, then we pad with enough dummy bids, or say we dilute the candidates pool. Then we randomly choose K bids from the padded pool, where this K is the block size. And finally, each confirmed bid pays R. Of course, those padded dummy bids will be ignored, and all payments are burned. Before we see why this is to SCP, I want to mention that when there are a lot of large bids, let's say when there are a lot of bids larger than M, and we select the posted price as half of M, in this case, we achieve optimal social welfare. So now let's see why this is approximate to SCP. Note that if the number of candidates is small, say, for example, in this case, the posted price is 5, and we only have these 3 candidates. Then we will pad dummy bids to make it T bids, so 10 bids, and we randomly choose 1 bid to confirm out of 10 bids. So for the big user, the probability that it is confirmed is just 1/10. Even if the small user drop out, the probability of it being confirmed is still 1/10. So in this case, dropping out does not help. However, if the number of candidates is very large, say in this case, all the bids are candidates, so we have far more than 10 bids as candidates. In this case, for the small user, if the small user drops out, then it indeed helps, but it cannot help too much, because the probability of the big user being confirmed can be at most 1/10, since the number of candidates is definitely larger than the predetermined threshold. So in this case, even if it drops out, it cannot help too much. So this is the core idea of this diluted posted price option. So in our paper, we also give the following more results. In our paper, we also give a characterization of infinite block size in the MPC-assisted model. And also, we show how we can achieve positive minor revenue, although in the talk, we only focus on the case where all payments are burnt. And furthermore, we also give other ideas of overcoming the impossibility result, which is approximate incentive compatibility. There are a lot of interesting open questions left by this work. So first, in this work, we only consider one-shot auction, but we know in reality, the auction is running repeatedly, so it is interesting to consider the repeated nature and long-scale strategies. Second, in this work, we are focusing on the theoretical feasibility of transaction fee mechanism. So we did not try to improve the efficiency or practicality. And it would be nice to figure out a way to make the MPC-assisted model practical. And finally, there are other interesting problems related to transaction fee mechanism. For example, in reality, the ordering of the transactions in a block actually matters. And of course, let's say in Ethereum, each transaction may have different size. We did not address these problems in this work, but it will be interesting to address these in the future. Thank you so much.